Hello, it is time to introduce the Heisenberg Group as part of the series of videos where we talk about the specific metric examples that are interesting in one way or another. I'm gonna only talk about the first Heisenberg group, which is commonly denoted by H1, and that is a space constructed on R3. So this is, I can't write equal or homomorphic or anything. Just as sets, for example, they both have R3 sitting there. And this space has recently been very intensely studied from analytic and geometric points of view. It's basically a place to go to test out new theories and try to see how far we can push the classical analysis in new territories. So it has even become to represent the field, the umbrella field name, non-smooth analysis. I remember attending a conference on non-smooth analysis, and almost all the talks concerned the Heisenberg group. So what is the first Heisenberg group? The higher dimensional versions can be constructed similarly, but of course R3 is easier to work with and also to draw pictures in and whatnot. So I'm gonna distinguish between the first two variables in R3, namely x and y, and the last one, t. So the last component is always special. So here x, y, and t are real numbers. And another useful way of thinking about them is that z is a complex number and t is a real number. Okay, so Heisenberg group is a Lie group, which in itself is a lot of structure there. First of all, there's a group, a multiplication action, which is, there's also a manifold structure, and this multiplication and inverse operators are C infinity, are smooth in this manifold structure. So we have to talk about how you multiply two points in this space. So if I take a point A, B, C, and I try to multiply it into x, y, and z, the result will be, of course, a new vector in H1, which is R3. And the way we do it is you just add here x at the first component. So it's similar to the group operator, the addition in R3 in the first two variables. In the third variable, you have this again. This would be just R3 with plus. However, the difference is this additional twist term in the last component. So this will be bx minus ay. Also, there's some variation. Some people have 1/2 instead of 2 here. And some people also have only bx, for example, or variants of this. So, but this is the one. They are ultimately equivalent, but homomorphic. But this group operation we want to take. So it's easier that if so the manifold structure, the smooth structure, the same as R3. So in this case, from the group multiplication, we can see that the inverse operator, the inverse of an element in this product, I have denoted it by just dot or nothing there, is actually coincides with the inverse in the usual R3 addition structure. So we see that both of these structures are C infinity. All these operations are smooth, say in x, y, and z, or a, b, and c. And therefore, with this structure, we have a Lie group. So what is special about the Lie group is that if you fix a vector at identity, you can translate it to every other point on the manifold with the group structures, with left transitions, and that's often very convenient to work with. So at the identity, which is 0, 0, 0, you can check that if you multiply 0, 0, 0 into any value, it doesn't change it. So at 0, 0, 0, we fix the usual vectors, so partial x, which is like this vector, partial y, which is this vector in the y direction, and partial t, which is this vector. So at 0, 0, 0, we fix the usual unit basis. The left translation by this action, the left translation of these to point x, y, and z will be, so if we transfer these vectors using left multiplication, that means we respect the group transition, we have no choice but to just see what those vectors will be. So the vector that comes from partial x will be denoted by this vector x, and at a point x, y, z, this will have again this partial part, but also it will have this additional partial t component. So this is just a real number coming from the base of this point, and of course these are the usual I and k vectors in the standard R3, if you wish. So the vector y, which is the transition of the j vector, will have this minus 2x partial t, and finally the left transition of the vector k will remain actually itself. So this will agree with the, if you translate it to any other point, it's again just partial t. So vector x, y pick up some partial t component, and that changes according to the base point, and you can see that the farther away from the origin you go, you're adding larger and larger vertical direction to these vectors. So let's try to draw some picture here. So this will be, say, my R3, if I can attach this point there. So let's draw, say this is partial x, and the left transition of this to some point, to some base x, y, z, will be again 1 unit in the x direction, but then 2 y units in the partial t direction, and if y is quite big, this becomes a large vector. So this becomes the left transition of that. So this is x at origin, and this is x at x, y, and z. Let's assume y is positive and quite large here. And if we translate this vector, this unit vector y, which at 0, 0 agrees with just j, its translation will be again 1 unit in this direction, but then you subtract, if x and y are both positive, you subtract a multiple of partial t, so this will be this. This picture is quite actually confusing, I admit, because this blue one is sticking out of the page towards us, but the red one is flat on the screen. And the partial t which is this green one, will translate to just itself. Okay, what is left the same is that these will always be linearly independent. They will span, again, the whole tangent space. And okay, so far, remember, I'm only talking about a Lie group with some smooth structure, but we haven't yet talked about a metric space, which is our ultimate goal. So to begin talking about this, a metric structure on this space, well, first of all, okay, we declare we equip R3 with a Riemannian metric, that is a dot product on tangent space. So a Riemannian metric is a rule to tell us how to dot product two vectors from the same tangent space. So if you are at this base point and if you pick two vectors, how do you dot product them? So we equip R3 with a Riemannian metric that I must say. So okay, by declaring x, y, and t to be mutually orthogonal unit vectors. And this will give us a left-invariant Riemannian metric. In fact, the way to construct this metric, how do you know such a metric exists? So the way to do it is actually start at the origin. You have just one vector tangent space that is a copy of R3, and you declare any three vectors you like, any three linearly independent vectors, to be orthonormal bases. And then by left translation, you can translate that dot product to any other tangent space. And that, by very construction, is a left-invariant Riemannian metric. So in this tangent space, at this base point, again, x, y, and z all have length equal to 1. Even this very long blue one is, by our construction, is a unit vector, and all of these are mutually orthogonal. That means x and y dot product is always 0 in this Riemannian metric, and x and x dot product with itself is 1, because this is just length of x to power 2 in this Riemannian metric. Okay, so once you have a Riemannian metric, you can give a distance function. Okay, one way to equip R3 with a metric, with a distance function. So here metric is in the sense of a metric space. I have talked about this double meaning for the word metric. So here G is a metric, is a Riemannian metric, but a distance function is also called a metric. So here we can equip R3 with a distance function by, okay, so we can say distance of xn. So here I have to take 2 points. So P is some point, Q is another point. So we can declare, so this is done whenever you have a connected Riemannian manifold. So infimum of length of gammas, where gamma connects x to y and is C1, so that it has a derivative. So length of a curve is integral of its speed. So gamma has a derivative gamma prime of t, and gamma prime of t belongs to the tangent space at gamma t. You take these, you dot product them in your Riemannian metric, you add them up if gamma is, say, parameterized from 0 to 1. So this gives the length of a curve between P and Q, and you look at the infimum of such value that you can get, and you declare it to be a distance function, and you can prove that this is indeed a metric in the sense that, well, d of PQ is greater than or equals 0, equals 0 if and only if P equals Q, and d of PQ is d of QP, this is obvious to prove, plus the triangle inequality. So you verify all of these so that this defines a distance. But there's nothing special so far about this, because all of this is standard Riemannian manifold things plus Lie group structure. But Heisenberg group is what is called a Sub-Riemannian. Space. So it's a Sub-Riemannian manifold. So how is a Sub-Riemannian manifold constructed? So here we looked at all the curves that joined a pair of points, and we infimized over the length. Sub-Riemannian manifold structure arises from restricting the collection of curves that we allow. So we allow only a certain subcollection of path from P to Q. So we will rule out some curves in taking that infimum. And what are the curves that we like? The allowable curves will be the so-called horizontal curves. So we will only like and allow horizontal curves in this space. But what is a horizontal curve? Definition. An absolutely continuous curve. You could also here say a Lipschitz curve. Gamma from some interval AB into R3. So this absolute continuity is in the usual metric of Euclidean sense. So in this sense, so you have a curve into R3 that is absolutely continuous. So such a curve is called horizontal if at almost every t in its domain. So being absolutely continuous means that the derivative exists almost everywhere. So gamma prime of t, so you have some curve, and at every t, here is gamma t on the curve, and it has a speed, a velocity that is gamma prime of t. So this gamma prime of t is special, is horizontal, and here horizontality is not like it's flat, has no elevation. This means precisely that it is in the span of the x and y vectors. Of course, these are based at gamma t, but sometimes I may drop them. So when you look at this very point, we have, sorry. So when you look at this very point, we have a copy of, I mean, not a copy of, we have the translation of x vector, we had the y vector, right? And then we had the t vector, our left invariant choice of vectors. So if this velocity gamma prime of t happens to be lying in the plane determined by only these two, and in other words, if we write gamma prime of t, which is a vector in R3, in the basis x at gamma t, y at gamma t, and t at gamma t, then the coefficient of t will be 0. So a curve, an absolutely continuous curve, is called horizontal if at almost every point the velocity belongs to the span of this special vectors x and y, and we don't need the t part. Okay, so not all curves obviously are absolutely continuous. So examples, gamma of t equals 0, 0 t. A curve that just vertically goes up is not horizontal because its velocity is actually only pointing in the direction of t, and it doesn't actually pick up anything from x and y vectors. So this is not horizontal. And on the other hand, a curve like t 0, 0 is horizontal. In this case, it happens to be horizontal in the literal sense that it lies flat in the xy plane, but not all horizontal curves are horizontal in the literal Euclidean sense, as will be very clear from what then follows. Okay. The Carnot-Carathéodory distance on H1 is given by, okay, distance, this one, this time CC, Carnot-Carathéodory, of 2 points PQ will be infimum of the length of gamma such that gamma is, okay, joins P and Q, but now we only allow horizontal curves. It's horizontal and joins P to Q. Okay, so this is definitely bigger than or smaller than the previously defined Riemannian distance, because we now have a smaller collection of curves to infimize over. So the more curves you have in the collection, the infimum can potentially get smaller. And we will see that this is actually strict in most cases. And we are not going to talk about this distance again. That is not the most interesting distance function on this space. Okay, so that will be the definition of DCC. It's easy to prove properties of DCC to see that it is a distance function. For example, it's never negative, obviously. It's 0 if and only if p equals q. Triangle inequalities is pretty obvious because if you have a horizontal curve from p to q and then from q to s, you can concatenate and get a horizontal curve from p to the third point. All of that are good, but it is not easy to show that actually DCC is well defined. So this is actually a common mistake, that sometimes you define something and you can easily prove a lot of things about it, but you must always check that what you write down really is meaningful and makes sense. For example, is there even one curve connecting P to Q? Because if this collection is empty, then the infimum will be infinite. And then DCC is not a distance function, because for every pair you should give out a real number and not infinity. So the biggest question will be, given P and Q, is there always at least one horizontal curve joining them? So again, once you get past this well-definedness, the rest will be easy. But this is not at all trivial, because you can travel only in certain directions. For example, let's say P is sitting at 0. You can take off at 0 only in the literal horizontal direction. That's a funny music that plays every 8 p.m. here. I don't know where it comes from. So you have this, and these are your vectors x and y. And their span will be just the usual xy plane here. So a vector that is horizontal and passes through the origin can take off only with a tangent contained in this plane. So even if your end goal is to reach a point Q up here, you can't just connect it with a straight line, because the tangent will not be in the horizontal direction. So initially, you have to take off somewhere tangent to this plane, for example, like this, where the tangent looks like that. And then hope that you can then spiral up and reach that point Q that you wanted to reach. Now, if you didn't have this twist in x and y, if your vectors x and y and t were just partial x, partial y, and partial t, this would actually be impossible, because to remain in the span, that would mean that your tangent is always looking this way. So there's no way you can add this twist and go up. But the point is, these vectors themselves are twisting. So that is the whole point. That will finally allow, so this was 2y ddt, and that had negative this. Whatever it had, this additional part which has exactly the vertical direction is the whole difference. And this is to justify things and explain why it is possible to always be in the span of x and y and still travel vertically. But it's way far from being a proof. The proof, of course, is a famous theorem, and which says, yes, you can always do this, and that is called Hormender Cho theorem, sometimes called Horman-de-Cho connectivity theorem for obvious reasons. So we need this big theorem to make sure that we are taking an infimum over a non-empty collection of curves. So there is always at least one curve, one horizontal curve joining P and Q, and therefore this infimum is a well-defined real number. And there's actually more in this theorem, and that is in our case, this will say that the Carnot-Carathéodory distance of P and Q is so there exists some constant bigger than 1 such that this is bigger than 1 over c, a distance of P from Q as if they were in R3, and less than c, distance of P and Q to power 1/2, again in R3. This is not exactly correct. I must say, for every compact U in R3, there exists some positive C, which only depends on U. Okay, such that this. Yeah, that is also usually proved along with this connectivity result. This, talking about compact sets, this concerns small values of P minus Q to R3, because this is root and this is not root, and this becomes bigger than that only when P minus Q distance is smaller than 1. And that C helps to deal with like not strictly bigger than 1 cases, but one thing that we see here, the upper bound is sharp, and in fact in our case, if you have 2 points along here on the vertical distance, so this is, let's say one is the origin and the other one is 0, 0t, then the Carnot distance of P from Q is either equal, depending on the parameters, or proportional to root t. And this is much larger than just t for t small, because if you divide them, actually you get 1 over root t, which belongs to infinity. So in the Carnot distance from here to here, infinitely longer compared to a Euclidean distance. So in the Euclidean distance, their distance is just t, but in the Carnot distance it's root t. And as you can imagine, if you are quite horizontally away from each other, then it is indeed comparable to the Euclidean distance. So both this side and this side are kind of optimal. Okay, and another way of seeing why this happens when points are vertically from each other is exactly because horizontal direction is completely hates this. This is the most non-horizontal direction that you can travel, but for the curves to connect, they have to have horizontal tangents. And there are nice pictures here and there of the geodesics or shortest curves in Carnot in this metric, and actually the result we know is that the geodesic, the shortest curve that joins P to Q, number one, it's not unique, there are many of them, Secondly, they are curves like this, and they have this feature that their projection onto the xy plane, like vertical usual projection. If you project these down, the curve down to xy plane, they span circles. And the circles are optimal with respect to how much area they contain versus their perimeter. And that has a connection to this geodesic problem here. So the problem of shortest curve in this metric is equivalent to the problem of what is the biggest area that a curve can enclose with the same perimeter, and the circle is answer to that. There is a paper by my previous advisor, Piotr Heiwash and Scott Zimmerman, where in all dimensions they characterize all the geodesics in the Heisenberg group. If P and Q are not exactly vertical from one another, then the geodesics are indeed unique. But this feature that their projections enclose circles is still there. In the higher dimensional case, it's not one circle, but a collection of circles projected on various pairs of axes. Okay, so if you believe in this connectivity result, then you believe that this indeed defines a distance function on our H1. And then there's this result here which shows that this distance is truly different from the Euclidean distance. Okay, so let me see. There's of course a lot to be said about the Heisenberg group, but let me maybe end with this. This is another result that says for every U compactly contained in R3, there exists a C, again depending on U, such that if P is some Z and T, then the Carnot distance of P from the origin, which is 0, 0, 0. And by left translation, actually, this is it, to know the distance DCC between any P and Q, it is enough to actually know the distances to the origin only. That's not a surprising claim, but so we saw how much went into defining DCC. So explicitly calculating distances in this metric is almost impossible. Therefore, this theorem is a great way of estimating that. So it says that if you, so remember this is a complex number here, so Z you raise to power 4, you raise T to power 2, and then you take 4th root. So the distance, the Carnot distance is no more than this number. On the other hand, there is also this one that says, okay, same value to power 1 over 4. In other words, these two quantities are by Lipschitz comparable, which is great. So the same value on both sides, and only up to this constant they are comparable, and the constant is universal. This quantity is what is called the Coronian metric, or Coronian norm, because is again z and t. Its norm is z2 4 plus t2 squared. It's actually not very easy to calculate and confirm that this is in fact a norm, because you have to prove the triangle inequality. But the amazing thing is that this is comparable to the distance that was constructed after so much structure was called in. Okay, let's mention things. So Lipschitz functions, for example, from the Heisenberg group into R are very different from, in general, the class of Lipschitz functions changes drastically because the metric changed drastically. So a function being Lipschitz from H1 to R1 is not always the same as the same function being Lipschitz as if it was from R3 to R. Often it's quite confusing because these as sets are the same and this is built on the same thing. So whatever you have, you can always go back and interpret this in terms of R3, but we have to also keep in mind that we're talking about a distance function, a different distance function, and different group structure. The unit balls in DCC metric are not convex. So, and this is kind of very different from what happens in the Euclidean case. The unit balls, again, there are some nice pictures in the internet, but so let's say this is the sphere. So every point here has distance 1 to the origin, but then when you reach the t-axis, there is this dent inward, and then it flattens out and it connects like this and goes back. Of course, by symmetry, you have it in all directions and also down here. So the unit balls are quite strangely shaped, and if you scale down, instead of unit radius you allow epsilon radius, they become even nastier, because remember we said that in the t direction it's very long, it's very costly to travel in t direction, so you pick up distance pretty fast. So the balls of smaller radius look even flatter, because here, if this is epsilon much, in this direction you have to go only root of that much. The ratio is root of that much, which is much smaller than would be in Euclidean case, so they look even flatter. Balls are flatter for small radius. And the list goes on. There are many things change, many things remain true, and that's why Heisenberg Group has been so important in analysis and geometry, because while many things are still there, other things have changed. So we can ask, do we still have area formulas? Do we still have co-area formulas? What is even rectifiability on this space? And that has been a kind of less than completely solved question. There have been variants and different tries at definition. Even like what should be a rectifiable set in this space is not really clear. And the themes of papers have been to show that the rectifiability definition of this paper is equivalent to the rectifiability definition of that paper. And again, this H1 is only a very particular example. You have Hn, but also you have what is called Carnot groups, and these are examples of Carnot groups. So of course people, when study deep questions they don't just do with H1. They are more interested in more general things, but H1 in itself is still interesting, and there are some open questions that are open even in H1 case. I hope you enjoyed this quite involved example. It required some little bit of, not some, let's be honest, quite good deal of Riemannian geometry, manifold theory, and a little bit of Lie group. If you didn't know Lie groups, you could just try to guess what left translations are. So they are a way of moving in the group using multiplication. If you have any questions, please put in the comments. Meanwhile, please, those of you who have just joined in, consider also hitting that subscribe button so that I know there is still interest in the stuff we put out. And if you have any other metric space example that you're really curious about, please again tell me and I can make videos about those. Until next video, see you.